Previously, we learned how to write parametric equations for circles, both static ones and rolling ones. The next step is going to be tracking circles that roll within other circles, then tackling a circle within a circle within a circle. These are slight variations of Fourier circles. In the first problem we're looking at, one circle with radius b will be rolling around within a bigger circle with radius a. The smaller circle is initially centered around the x-axis with point P at coordinate a, 0. Like always, our first step is assigning variable theta. In this case, theta will be angle TOX. This way, theta will be 2 pi when the circle rolls one full rotation. Segments QB and OX are both horizontal and thus parallel. That causes angle TOX and TQB to both be corresponding angles, and that makes them congruent. Solving this equation uses the same trick as last time. Arc TP must equal arc TX since the two circles touch at every point. Arc TX will always equal angle TOX times segment TO, which equals A times theta. Arc TP equals angle TQP times TQ. We don't know angle TQP. Let's call angle BQP beta. That makes angle TQP beta plus theta. Then we get arc TB is equal to B times theta plus beta. Setting TP and TX equal, we can solve for beta in terms of theta. Next up, let's solve for P in terms of different segments. X equals Q sub X plus AP. Y equals Q sub Y minus AQ. OQ is always TO minus TQ, which is A minus B. That makes Q sub X equal to A minus B times the cosine of theta, and Q sub Y equal to A minus B times the sine of theta. With right triangle trigonometry, we can see that AP is B times the cosine of beta, and AQ is B times the sine of beta. From this, we can use algebra to simplify this all together. I was fascinated by the different shapes made when the radii are changed. When the bigger circle is twice as big, it only traces out a straight line. Kinda mind-blowing, huh? When it's 3 times, there's a quasi-triangle. 4 times, a quasi-square. 5 times, a quasi-pentagon. Here's what happens when the radii increase, but the number of rotations is constant. For the next problem, let's add a second circle with radius c. Surprisingly, finding the path of point P isn't actually all that difficult. If the middle circle has center Q, Q sub X equals A minus B times the cosine of theta, and Q sub Y equals A minus B times the sine of theta, just like what we proved before. Now imagine that Q is at the origin. This should feel familiar. That's because the relationship between Q and P is the exact same relationship that was between the origin and P in the first problem. That means that we can use the same equation, but we'll have to replace all the A's with B's and all the B's with C's since the radii are different. Let's also replace theta with n times theta. This way, we can analyze what happens when the circles are moving at different speeds. What I find interesting is that the number spike seems to correspond to how many times faster the inner circle moves. But regarding the radii, it's much less noticeable how they affect the shape of P's path. I've included some examples for you to look at. And on that note, I challenge you to figure out what the different patterns are.